In this video, I'm going to show you how to perform binomial expansion using Pascal's triangle. Remember, binomial expansion just involves multiplying out a binomial that is raised to some power, say a plus b squared. When you multiply that out, a plus b times a plus b, you get a squared plus 2ab plus b squared. And we can also do this for a plus b to the third power. We could do this again by multiplying it out. Using our result earlier, a plus b squared is just a squared plus 2ab plus b squared. So if we multiply that by a plus b, we'll get the expansion for a plus b to the third. And when you do that multiplication, you get this expansion, a to the third plus 3a squared b plus 3ab squared plus b to the third. Okay, so what if we wanted to continue doing this? What if we wanted to find a plus b to the fourth? We can expand that out again. We can just multiply. We can do a plus b times the result that we got for a plus b to the third. But you can see that this is starting to take up a bit of time and effort. This term just keeps on getting bigger and bigger, and as we keep on multiplying that by a plus b, it becomes more and more trouble to multiply out. So why don't we look and see if there's a pattern that we can find in the results so that we don't have to go through all the work of multiplying a plus b to the fourth. Well, look at the first terms. First term is a squared originally, and then it goes to a cubed. So can you guess what it's going to be for a plus b to the fourth? Well, looks like the exponents are just increasing by 1, so I think it'll be just a to the fourth. Okay, and now how about the next term? So in a plus b squared, it's 2ab, and then a plus b to the third is 3a squared b. So what do we notice here? Any patterns? Well, first of all, look at the exponent on the a. The exponent on the a is 1 less than it was than the first term. So first term was a squared, then it goes to a to the first power. It's like a to the first power here. And then it goes a to the third, then a squared. So we should expect an a to the third exponent here. And you'll also notice that the exponents in each expansion always end up adding to the same power. So this is b to the first, and 1 plus 1 makes 2. There's also 2 here. This is b to the first. This is a to the first. All of these sum to 3. 2 plus 1 is 3, 1 plus 2 is 3, 3 is 3. So we should expect that the exponents here should add to 4. So we've got a to the third, and then b to whatever power we have to add to make 4. So 3 plus 1 makes 4, so b to the first. And there's probably some coefficient in front multiplying it. 2, 3, maybe it's 4, but why don't we just leave it blank for now, because that might not be enough for us to tell a pattern. So plus something, leave a blank coefficient. Okay, and we'll just do the same thing for the next term. So plus something, and then again the a is decreasing in power, so it goes 4, then 3, then 2, and the b has to take on a power so that the sum of exponents adds to 4. So 4, 3 plus 1, then 2 plus 2. Okay, and then we have to have another term plus something multiplying that other term, and then the a power this time, 4, 3, 2, a to the first power, and then b, well, the power has to add up to 4 when it's combined with the a to the first. So 4, then take away 1, that's 3. Great, so 3 plus 1 makes 4. You can also notice that b is increasing power, 1, 2, 3, and that's consistent with what we had before, 1, 2, 1, 2, 3. Okay, so now we're ready for the next term. So the next term, the next term is just the last term here, because a is to the first, and we're running out of powers for a. A to the first there, we've just got 1 more term. A to the first here, just got 1 more term. So this next term will just be a b term. And we've never had a coefficient on the b term, so we probably shouldn't expect to have a coefficient. So we'll just have b to the fourth power, because 4 is what all the exponents are adding up to here. Okay, so we've got most of it done, but we need to find the coefficients. So how do we do that? The answer is Pascal's triangle. Pascal's triangle is constructed just using the coefficients from our binomial expansions. So let's look at our binomial expansions. This time we'll start with 0. as an exponent just to be complete. A plus b to the 0 is 1, because anything to the 0 is just 1. And so we put that at the top of Pascal's triangle. Then a plus b to the first is just a plus b, and we're going to write those coefficients very explicitly. That's 1a plus 1b, so we'll put 1 and 1 in the triangle. Then a plus b squared, coefficients are 1, 2, 1, so the next row in the triangle is 1, 2, 1. Then a plus b to the third, 1, 3, 3, 1 are coefficients, so put those in the triangle. And then a plus b to the fourth, we already figured out what the a to the fourth, a cubed, b, a squared, b squared, we figured out all of that, but we just needed to figure out what are the coefficients. And so we're going to leave those blank in the triangle and see if we can notice a pattern in Pascal's triangle. Okay, so looking for a pattern. Do you see any patterns in here? Well, hey, look at that. So 1 plus 1 makes 2, and then 2 plus 1 makes 3. Also 2 plus 1 makes 3 here. It looks like every entry of the triangle is the sum of the two entries above it. So this entry should be 1 plus 3 is 4. And then this entry here should be 3 plus 3 is 6. And then this entry here should be 3 plus 1 is 4. So now that we see what the coefficients are, we can put them back into our expansion. 4, 6, and 4. If we wanted to find the coefficients for a plus b to the fifth, we could just do that by continuing Pascal's triangle. The next row, we'd have 1s on either end. And then so we'd have an entry, an entry, an entry, an entry. And we get each entry by just adding the two entries above. So 1 plus 4 makes 5. Then 4 plus 6 makes 10. Then 6 plus 4 makes 10. And then 4 plus 1 makes 5. And so these would be our coefficients when we expand out a plus b to the fifth. And we could keep on going on and on, continuing forever until we want to or need to stop. We could go on as long as we want. So the next row, for example, would be 1 plus 5 is 6, then 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5, 15, 5 plus 1, 6, and yeah, we could just keep on going on and on. Okay, so now here's an example. We want to find the binomial expansion of 1 plus x to the fourth. And let's do this the fast way using Pascal's triangle. So first of all, 1 plus x to the fourth. What row of Pascal's triangle does this correspond to? Well, the first row here is really like the 0th row. That corresponds to the power of 0. And then the second row corresponds to the power of 1. So you can really count the rows starting with 0. 0, 1, then this is 2, this is 3, this is 4, this is 5. You can also notice that the exponent matches up with the second entry here, 1, 2, 3, 4, 5. So either way you look at it, this is the row that we want. 1, 4, 6, 4, 1. This corresponds to a binomial with the fourth power on it. Okay, so this tells us our coefficients here. 1, 4, 6, 4, and 1. Okay, so let's go ahead and fill in these coefficients. Okay, so put pluses between them. And okay, so how about the first one? The first one is just 1 times the first term to the fourth power. And then the second term doesn't appear. And then the fourth power just gets decreased to the third power in the next term. And then the second power in the next term. And then the first power in the next term. And then it doesn't appear in the last term because that's just to the 0th power. Okay, and then how about the next term? So the x term, that doesn't appear in the first term here, but it does appear in the second term. We have to have an x to the first power because the exponents always have to add up to 4. And so we can increase into the next term. This is x squared, so 2 plus 2 is 4. Then the next term should be x to the third, 1 plus 3 is 4. And then the last term will just be 1x to the fourth. So there we go. Now we can simplify this a little bit. 1 to the fourth is just 1, so this is just 1 times 1, which is just 1. And then plus 4, 1 to the third again is just 1, so 4 times 1 is just 4. And then we've just got an x here, plus 4x, and then plus 6 times 1 squared, again just 1, so just 6, x squared. 4 times 1 times x to the third is just 4x to the third, and then 1x to the fourth, we can just write that as plain old x to the fourth. And there we go. There is our binomial expansion of 1 plus x to the fourth. Here's another example. This one's pretty similar to the previous example, except it's a little trickier because now we have bigger numbers, 2 and 3. Also, there's a negative sign here, and the second term here is actually two terms multiplied, the 3 and the x multiplied. But nevertheless, let's go ahead and proceed like usual. But like usual, usually we have a plus sign in between. So before we start out with the actual expansion part, let's rearrange this binomial to have a plus in between the two terms. So how we can do that is we can put that subtraction sign, we can change that into a negative on the 3x. So let's write that out. So that's 2, and then we're going to put a plus sign and change the 3x to negative 3x. So it's equivalent to the original binomial, but now there's a plus in between the two terms. 2 is like our a term, negative 3x is like our b term. That's all to the 5th power, and now we are ready to proceed with the expansion. So 5th power here. So let's look for the 5th row of the triangle. Remember, first row is actually the 0th row. And the easier way to see this is just count the second entry, 1, 2, 3, 4, 5, go to where it's a 5, and that is the row that we want to use. 1, 5, 10, 10, 5, 1. So these are our coefficients in our binomial expansion. Let's write them out. So 1, and then 5, and then 10, and then 10, and then 5, and then 1. And we're going to be adding up all of these, but we're leaving some space because we have to write down the multiples of these terms here. So starting out with multiples of 2, and our first term, we have 2 raised to the full power of 5, and then the power just decreases going forward into the other terms. So next term is 2 to the 4th, decrease that 5 down to 4, and then decrease the 4 down to 3, then decrease again to 2, decrease again to 1, and then it just doesn't appear in the last term. Now the second term here, the minus 3x part, that is following the opposite pattern. It doesn't appear in the first term, but it does appear in the next term, negative 3x to the 1st power, because we need 4 plus 1 to make 5. We need that exponent of 1 to ensure that the exponents sum to 5. So now the exponent just increases, so negative 3x squared, again they sum to 5, then just negative 3x to the 3rd, keep on increasing that exponent, negative 3x to the 4th, and then negative 3x to the 5th. Okay, and now we just have to compute this. This is a bit of computation work, so it's really handy to use a calculator for this part. But before we jump into the actual calculations, let's just rewrite this once more, making sure to distribute this exponent on the minus 3x terms. We have to distribute that to both the negative 3 and the x. So let's just write this again, simplifying it so we can just look at straight up numbers for the computations. So this first term is just 2 to the 5th, then plus 5 times 2 to the 4th, then times negative 3 to the 1st power, then times x to the 1st power. And then plus 10 times 2 to the 3rd times negative 3 to the 2nd power, then times x to the 2nd power, and just continue writing it down like this. Negative 3 to the 3rd, x to the 3rd, plus 5 times 2 times negative 3 to the 4th, x to the 4th, plus 1 times negative 3 to the 5th, x to the 5th. Okay, 1 is a 1, not a parenthesis. Okay, and then we can just go ahead and compute all these coefficients. all these things, just punch it into the calculator, and what you get is you just get 32, then the next one is minus 240, so that coefficient there, then just x to the first power, and then plus 720 x squared, then minus 1080 x to the third, then plus 810 x to the fourth, then minus 243 x to the fifth. And there we go. That is our result. That's our binomial expansion. And we are done. Here's our last problem here. We want to find the coefficient of x to the third in the binomial expansion of 3 plus 2x to the fifth. Now, one way to do this problem is just to go ahead and do the whole binomial expansion and then just pick out the x to the third term and look for that coefficient. But as we saw in the previous example, that takes a bit of time. So why don't we look at this a smarter way? So x to the third, let's not worry about our coefficient just yet. We'll write our coefficient, just say a box here, and then the first term, 3 to some power, and then the second term, 2x to some power. All right, so if we know that the coefficient should be of the x to the third term, we need an x to the third to appear here. So that means this power here has to be 3. Okay, and if this power here has to be 3 to give that x to the third, then what does that power have to be? Well, the exponents always have to add to 5. So this is 3, and then if we add this exponent, it should make 5. So this exponent needs to be 2. That way 2 plus 3 makes 5. And okay, so how about the coefficient in front now? So Pascal's triangle, again, we're working with an exponent of 5, so we need to go down to the row that has a 5 as its second term. That's this row, and let's label our coefficients here. The first one is the x to the 0 coefficient, because that's when we don't include the second term at all. And then we've got an x to the 1 coefficient, and then an x squared coefficient, x to the third coefficient, x to the fourth, x to the fifth, and the x to the third coefficient is what we're interested in. So that is just 10 here. There is our coefficient that we want. So 10 in front of here. And now let's just multiply it out. So this is 10 times 3 squared is just 9. And then 2x to the third, well, 2 to the third is just 8. And then we've got x to the third. And if we multiply this out, 9 times 8 is 72, then times 10 is 720 x to the third. And we want the coefficient of the x to the third. So this is our answer here, 720. That's the result. So now we see that Pascal's triangle is pretty useful for computing binomial expansions. And in the future, we'll see how to apply binomial expansion to approximate values of exponentiated decimals. And we'll also learn some new notation that we can use to write, say, the kth entry in the nth row of Pascal's triangle.